So in this lecture, we will start the theory of constraint optimization. And first with the geometry and algebra of constraints. So first we will try to understand constraint functions, how they affect the constraints, and then an important condition called constraint qualification. And then we will talk about algorithmic strategies on constraints or algorithmic strategies to handle constraints. So in the unconstrained optimization problem of n variables, the domain was the complete n-dimensional Euclidean space. Okay. In constraint optimization, the domain is typically described by equality constraints of this kind and inequality constraints of this kind. Now, the way we work out the official theory, it is important that all equality constraints are brought in this form, that is taking everything on one side and equating that expression to 0. Similarly, inequality constraints need to be brought in this form by taking everything on that side, which must be negative or 0 when the constraint is satisfied. Okay. So these functions are referred to as constraint functions. Okay. So a solution point x satisfying all these constraints is called a feasible solution, and another which violates at least one of them is called an infeasible solution. Still it is called a solution, okay, because the entire space is called the solution space. So for a given point x, a constraint may be violated or satisfied. If it is satisfied, then it can be active or inactive. Okay. So you say that an inequality constraint is violated when the constraint function evaluates to something positive, and an equality constraint is easy to violate because if its value turns out to be non-zero, it is violated. Okay. If it is not violated, then it is satisfied. And there are two ways of satisfying a constraint. A constraint is called active when this evaluates to 0. Okay. And this also evaluates to 0. Okay. So in that case, it is called active. So an equality constraint, if satisfied, has to be active. Okay, because on both sides of the surface, both sides of this surface, it will be violated. Just on it, it will be satisfied. Inequality constraint can be satisfied but inactive, where this is less than 0, not equal. Okay, so then it will be satisfied, actually happily satisfied. So and it will be, the point will be an interior point so far as that particular constraint is concerned. Okay. There is no way an equality constraint can be active. It has to be violated or inactive. So equality constraint cannot be inactive. It is either active and satisfied or violated. Okay. So you can see that an equality constraint in a way reduces the dimension of the problem. So in n variables, if you put one equality condition, then n minus 1 variables remain independent. Okay. In fact, you can find out n minus 1 parameters in some cases, in terms of which you can express all the n variables. Then effectively it becomes an n minus 1 dimensional problem. In the case of inequality constraint, nothing of that sort takes place. the dimension of the problem remains the same, but part of the space gets cut off. Okay. Actually, the positive side of this function gets cut off. Okay. So a constraint function set equal to 0 defines a hypersurface. In 3D, an equation in 3D space, an equation among x1, x2, x3 will give you a surface xyz, right? The same thing when generalized to arbitrary number of variables in dimensions is called hypersurface. Okay, so a constraint function set equal to 0 defines a hypersurface in the space of x. A feasible point can lie only on that hypersurface for an equality constraint, and for an inequality constraint, it can lie either on or on one side of it. Okay. Now, the active set, this is a term actually. Okay. The active set of constraints at a point will include then all the inequality constraints for which this is 0 and all equality constraints anyway. The inactive set, that is those inequality constraints which are satisfied and satisfied with a margin, that is for which gjx is less than 0, can be ignored for local analysis. Because if at that point gjx is negative, then around that there will be a neighborhood in which it will be so by continuity. Okay. So this is so far as the function values are concerned. Now we go to the derivatives. If the constant function is differentiable, in fact, the theory that we discussed, in that all the objective functions and constraint functions will be treated as differentiable. Otherwise, you cannot develop a theory on it with nice conditions and straightforward ways of implementing algorithms, but some algorithms still work. Okay. If a constraint function is differentiable, then you can talk about its gradient, first order derivative. Okay. And that you talk about only for active constraints, all HIs and those DJs which are in the active set. So its gradient defines the normal to the surface or hypersurface at that point. Okay. From that point, feasible directions can fall in the cone of feasible directions for which this is less than or equal to 0. That is, Gj is currently 0. If you evaluate rad Gj, then it gives a normal, actually outward normal. On that side of the normal, on which takes you to the infeasible region. Okay. Now, if you take a direction on the other side, then d transpose rad G will turn out to be negative. Okay. So this kind of inequalities will define what is called the cone of feasible directions. Why? Because one hypersurface goes like this, and on that a point is lying. If another such inequality constraint is active at that point, then that will have another hypersurface cutting through the first hypersurface and a third. Okay, so three such will define a cone kind of situation. Okay, more also for that you use the word cone. That is a generalization in higher dimension. So all these directions, continuously varying directions, which take you inside that inward cone, so those are feasible. And also feasible directions can be found in the tangent space. That is, for which the gradient is orthogonal to the direction. that is normal to the hypersurface, is orthogonal to D. That means D itself falls in the tangent space. Okay. So like this. So this and this. You will notice that for active inequality constraints, this actually can be considered contained in this in a way. But when we study the tangent space, then we include them with this. And when we study the cone of feasible directions, then we include them only in the cone. Okay. I mean, for equality as well as inequality. Because if you try to exclude equality from here, then there will be a messy discontinuity there. So these cases are included here as well as here. Now, for most of our local analysis, we will ignore inactive constraints, include active inequality constraints among the equality constraints, and add separate provisos for those aspects which are applicable only to inequality constraints. That means that for most of the theory, inequality constraints are actually pushed behind the curtain for frontal analysis, because inactive constraints are ignored. Active constraints are included among equality constraints, so they get treated along with equality constraints. And separately, as an appendix, we add certain issues because of the inequality constraints which were active, whose complete behavior did not get included as equality constraints. So those things which did not get included there, those issues we separately make note of. So that is the way we handle the inequality constraints. So now the tangent space or the tangent subspace can be looked at in two different ways. Say at a point X in a dimensional Euclidean space, the solution space, each active constraint will define a hypersurface, as we have discussed. So that is actually a surface of dimension n minus 1. The way in 3D space, a hypersurface is the surface itself, which is two-dimensional entity. Surface on the surface, if you go this way and that way, and then combine all directions which add this and that, then you actually cover all directions. The way on the surface of the Earth, you have latitude and longitude. Two coordinates describe the points on the surface. So in one perspective, you can look at the tangent subspace as this. For each such hypersurface defined by one constraint, you get a tangent space, which is a hyperplane, which is a planar section through the point X in the Euclidean space, which is of dimension n minus 1. Okay. So that is just like tangent plane in other ordinary geometry. Now, the tangent space denoted by this M of M such active constraints will be the intersection of M corresponding hyperplanes. Okay. And that will give you a subspace of n minus m dimensions. Think how it will work out in 3D, because 3D is something which you can relate to very easily. So in three-dimensional space, one surface has a tangent plane. Another surface through the same point has its own tangent plane. Okay. So two such surfaces will have two tangent planes and they will cut through a line. Okay. So the line turns out to be the common tangent space of these two surfaces together. And that means that if you try to draw a curve in 3D space through that point which lies on the surface 1 as well as surface 2, then it has to be along the intersection curve. And that intersection curve has a tangent, which will turn out to be a line. Okay, and that line is the intersection of these two planes. Okay, this is one way of seeing. Take the two tangent planes, intersect them. Okay. The other perspective is that do not bother about the tangent subspace for individual surfaces separately. First, consider the intersection of m such hypersurfaces themselves, curved, okay, corresponding to m active constraints, and then you will get a surface S of n minus m dimensions. Okay. Then consider its tangent, which will be a planar section of n minus m dimensions. Okay. So any curve in the intersection surface passing through the current point, this will be current, not C. Current point X will then have its tangent at that point in a direction that is in the tangent space. So these two ways you can look at the tangent subspace. Here, for each hypersurface, you get the tangent plane or tangent space, which is a hyperplane, and intersect those hyperplanes to reduce the dimension, but not by 1, but by m. In the other, you first intersect the hypersurfaces themselves, get the surface, and then surface has this dimension, then look at its tangent, which is a planar section of this dimension. Okay. So these two ways you can look at the tangent subspace. And the tangent subspace will appear in a big way in the analysis that we conduct further. Now we come to constraint qualification. What is this qualification? So if we collect the gradients of all the active constraints like this, grad H1, grad H2, etc., in columns like this, then this is a matrix of n minus m size. Each of these gradients has n entries and m such gradients are appearing. Okay. First order derivative you can talk about in another way. You could have taken the constraint functions all together as a vector function, okay, which is a column vector with h1, h2, h3 up to hm sitting as the entries. Since it is column, so that is transpose. And then you could say that now we evaluate its Jacobian. Vector function of a vector variable, so first order derivative will be Jacobian. So in the Jacobian, you would have this. And interestingly, here you would find that this grad h1 transpose would appear as its first row. Grad h2 transpose would appear as its second row. Okay. So from that you can connect and observe that this matrix that we earlier talked about is actually the transpose of the ordinary Jacobian. Okay. So this is something which has to be kept in mind in the theory that we discuss further. Now in 3D space, we will consider three cases of two constraints in each case, two equality constraints, and origin happens to be a feasible point in all the three cases, and at origin we will see the scenarios that develop in the three cases. Okay. These are simple constraint functions defining spheres and cylinders. Okay, so first we take the case in which you can see that this is a sphere. This equal to 0 will give you a sphere with center at 0, a 0 and radius a. The center is on the second axis. Here, similar sphere, same size, okay, but its center is on the x3 axis. Okay. So this is how they would look. So this is x1 direction, this is x2 direction, this is x3 direction. Okay. So the first, this one equal to 0 would give you this sphere with 0a 0 here at the center, and the second one will give you this sphere with 0 here, and both are passing through the origin, so origin is feasible. Now their intersection in this case will be a circle, okay, which will be of radius a by root 2, and it's a by root 2, yes, looks like a by root 2, yes, and its center would be somewhere here at 0 a by 2 a by 2. Okay. So there will be a circular intersection between the two spheres, and that circle is a one-dimensional curve. And this is all regular stuff. That is, as we discussed, that this is a surface and this is a surface, and the intersection is a curve, the tangent of which is a line, which is this x1 equal to g, x1 axis, there is a line which is a tangent. This is how you would expect the situation to unfold. Okay, so this is how you expect the behavior of two constraints in 3D space. Okay? The intersection is one-dimensional because from 3 dimension each constraint reduces one dimension. So the feasible space is one-dimensional. Its tangent is also one-dimensional. Good. And the other perspective of that would be that tangent to this surface is 2D, tangent to that surface is also 2D, and these two planes intersect and give you a line, which is one dimension. So whichever way you look at it, this is how it should happen. Now take the second case. Here we have the first one as a cylindrical surface. You see this. I have shown you the half cylinder. Okay, I've shown you the half cylinder. So actually this, the corresponding section through the origin here, which is a little behind the front surface that I have shown you. Okay, so that will pass through the origin. Okay? So this has its axis, this cylinder has its axis along the x1 direction passing through 0, 0, A. Okay? 0, 0, A, no, 0, 0, 2A, 0, 0, 2A, okay? 0, 0, 2A, because it is 2A here and 4A squared here. And x1 does not appear in this, and that is why along x1 you see this. Okay, the same geometry. Here also x1 does not appear, and there is another cylinder, okay, which is of half size. Okay. This one I have shown you fully. Okay. So on a bigger half cylinder, you just keep a tube like this. You can keep that. Okay. Now each constraint restricts feasible points to a cylinder. Okay. Cylinder, sphere, these are actually surfaces. Okay, not the solids. So together they restrict them to a line, which is also fine, one-dimensional. Each reduces to a cylinder, which is a 2D thing. Okay, two such 2D things intersect along a 1D thing, which is a line. In this case, the x1 axis. But till this point, everything goes fine. After that, things will go wrong. Why? Because this line, for this line, which is the common surface, when we try to find out the tangent, we find not one direction, but a full plane. The entire x1, x2 plane turns out to be the tangent space, which should have been of one dimension, but here it is of two dimensions. Okay? In the other way, you see that for this, you try to see the tangent plane, which is x1, x2 plane. For this little cylinder also, you try to look at the tangent plane. That turns out to be x1, x2 plane. If they were different, then their intersection could have been a line. Since they are same, their intersection is the full plane, and this is the problem. The tangent space is the entire x1, x2 plane, and that is of 2 dimensions. And this is the point where things go down. This is not what you expect from 2 constraints in 3D space. So around the current point x0, the 2 constraints are not behaving independently. They are behaving in a very related manner. So this is one problem. Another kind of such problem appears when we take the third case that we enumerated. Here the bigger cylinder, from this case we retain, and one of the spheres with its center at x3 axis we take from the first one. Okay? So what we are doing here, we take the bigger cylinder and the smaller sphere of the previous case, we just keep here on the origin. It can roll in this direction and roll on the cylinder, inside the cylinder like this also. Okay? And that is the problem actually. So this one restricts it to a cylinder, this one to a sphere. Okay? But together, rather than restricting the feasible space to a curve, they restrict completely to only the current point, origin itself, and nothing else. And this is not of dimension 1, this is dimension 0. Okay? And entire x1, x2 plane of dimension 2 turns out to be the tangent space. Okay? So this is also not a very regular case. Okay? So the joint action of the constraints is irregular. So locally, here also the 2 constraints do not qualify as independent. So such local degeneracies disturb the regular pattern of the theory, the elegance of the theory, smoothness, okay. And even for algorithms, as they operate, they turn out to make the systems ill-conditioned, okay, or singular. So degeneracies come, things will become singular. So this is a constant problem in the case of constraint optimization, and therefore, in order to safeguard against these things happening, we have a standard criterion to test the combined first order behavior of constraints at a point. And in that test, you will see that we use the words constraint qualification, regular point, irregular point, and so on. Okay. So constraint qualification condition, or the full name is linear independence constraint qualification condition. So the way you call your friend as Pawan, and his full name is Pawan Kumar Sharma. So this is Pawan and this is Pawan Kumar Sharma. Okay. So the full name is linear independence constraint qualification condition. Sometimes it is said as LICQ. The way your friend can be abbreviated as PKS. But for continuous discussion, we can use Pawan. That is constraint qualification. So the constraint qualification condition requires these gradients of the active constraints at the point to be linearly independent, or this matrix which we constructed should be full rank. Now it cannot have rank more than n because it is an n by m matrix. M is never greater than n, typically it is less. So the full rank means rank should be m, not n. Okay, not the dimension of the problem, but the number of active constraints at that point. So if all these are linearly independent, then m columns are linearly independent, and in that case it is of rank m, that is full rank. In that case, you say that constraint qualification condition holds. Okay. So in that case, these gradients provide a basis for the normal space, that is space, that subspace which is normal to the tangent space, okay, orthogonal to the tangent space. And a feasible point satisfying this condition is said to be a regular point. And that means an irregular point will have trouble. So at a regular feasible point x, you can express the tangent space like this. Elsewhere also you could do that, but in this case, for every direction in the tangent plane, y will be unique. Okay. So a general vector in the normal space then will be a linear combination of these gradient vectors, and that can be shown as this. Okay. So this is m dimensional, and this will turn out to be n minus m dimensionals, n minus m dimensional. Together, the two orthogonal parts will constitute the full solution space, the space of all directions in the Rn. Okay. So formulations and algorithmic steps can be conducted smoothly around a regular point. Around an irregular point, this will have rank deficiency, and things will go wrong. We will see how things go wrong later when we discuss algorithms. And if the dimension of this turns out to be less, then the dimension of the normal space will turn out to be more. Okay, and it will not be it will not turn out to be properly expressed like this. Okay, so or if more of these turn out to be linearly dependent, then the tangent spaces will actually have more dimensions, which will not be possible to completely describe in a smooth manner with this kind of arrangement. Okay. Y will be basically non-unique. If an operational feasible point happens to be irregular, that is, if you find that this does not have rank m, it is of rank less rank, then what to do? Then that column of it, which can be expressed as a linear combination of some others, you can drop that temporarily from that, and then say officially declare it as a case of that constraint not being there. Okay, so this is how you handle it. So for the analysis of the tangent space, you then drop this particular column from grad hx temporarily, and that can restore regularity for the purposes of analysis. Now, inequality constraints require some arrangement to handle them, because as you consider different points in your discussion, at some point someone is active, at some other point someone else is active. Okay, and the combination of constraints which are active keep on changing from one point to another. So which ones to include in the equality constraint? That requires a bookkeeping of the active constraints. Okay, so as an algorithm moves from one point to another, one needs a framework for this exclusion of inactive constraints, and it should be inclusion. One of them should be inclusion. So inclusion of active constraints along with equality constraints, which are always active, and exclusion of the inactive constraints as background material. Okay, so there are two strategies for handling this. One is called an active set strategy. For that, what you do is that you just maintain a little set which has a few numbers. Say there are 10 inequality constraints, out of which constraint number 1, constraint number 3, constraint number 7, constraint number 9 are currently active at the current point. Then you maintain for this iteration, for this step, a little set of those four numbers, 1, 3, 5, 7. Then you take this one step and go to another point where 3 is no more active. So you make it 157, 179. But then you notice that 6 has become active. Then you make it okay, fine, 1679. Okay. So this way, from one point to another, you keep on updating this little set called active set, which is a set of indices of the active constraints, and refer to that, consult that for doing most of the business. In the other strategy, what you do, which is called a slack variable strategy. Every inequality constraint like this is converted to an equality constraint in the beginning. Okay, like this. So whatever equality constraints are already there, some more equality constraints you add by putting this function plus some variable yj equal to 0. And you call this yj as the slack variable. That is a margin with which it is satisfied. Okay. So all the variables together, original variables x and the slack variables y, all of them, those n plus L of them, then make the solution space. The dimension of the official solution space increases. And the original inequality constraints then reduce to these non-negativity constraints, that these yj's should not be negative. Okay, they are positive or 0. And that's it. Now the relationship between these two strategies is very simple. A particular yj being 0 means that there is no slack, no margin anymore, and that constraint has become active. Okay? So an active constraint has the corresponding slack variable 0. So this is a connection between the two strategies. So algorithms typically handle one of these strategies to manage it. Now, in this lecture, whatever we have discussed, let us have a quick summary of them. So equality and inequality constraints together define the domain and affect the solutions in several ways. And formal analysis are conducted mostly around regular points, satisfying the constraint qualification condition. The bookkeeping of inequality constraints at solutions can be managed using the active set strategy, or to an extent avoided by using the slack variable strategy. Both are actually in use. In the next lecture, we will study first order conditions of constraint optimization, in which the geometry algebra of constraints, constraint qualification, these things will be utilized there. So currently we stop here. Thank you.